So there is these two possibilities. And then before you leave for lunch, we are going to distribute a map with some restaurants around. You can have here where we have the reception yesterday, but it's not very big. You can walk in the direction of Sugarloaf. There you have some restaurant. There is the shopping center. So you'll be plenty of possibilities. And you should be back at 3 o'clock. And the coffee break in the afternoon will be served in the restaurant, and it will be more things to eat. Okay?
Okay. From Boston University, he's going to give 3 lectures on the quantum Hall effect. So Claudio has told me that he would like to have many questions, just like in the previous session. So please don't hesitate to ask questions. Claudio, please.
Okay, thank you, Eduardo. Okay, so I'm going to tell you about the quantum Hall effect. And one thing I should say about the quantum Hall effect is that it is many things depending how you look at it. You can look at it from the point of view of metrology, and I'm going to discuss a little about it. I'm going to write down for you what basically square over age is, many decimal places, and you're going to appreciate how many of those decimal places one can get, and why it became the standard for resistance, the SI standard for resistance. It also brought about many interesting ideas in condensed matter physics. I should say not condensed matter physics, for sure in physics. We're going to discuss in the second set of lectures in detail fractionalization, how less is different. How you can actually start with a system that has only electrons, and have elementary excitations that have the fraction of the charge, that have fraction statistics, and what it actually means. We're going to discuss if we lived in low dimensions, if we lived below 4K, then we would look at a very different universe. And in that case, the electrons would look like high energy physics for us. And in the third set of lectures, I'm going to tell you some of the recent developments, because, see, the quantum Hall effect is 25 years old, and one would say, okay, it's totally understood. There are many things that are, I would say, well understood. I would put BCS superconductivity and the quantum Hall effect as probably the best understood many-body problems. And our level of understanding is way above many others, with the exception of, I would say, problems like in low dimensionalities, like the Curie problems, like the Kondo problem. So we have much to learn from the fractional quantum Hall effect. But recently, since it's a never-ending source of surprises, there are many theoretical developments and now a quest for experimental probes to look at those. The notion that you have quasi-particles that not only have fractional statistics, but they have non-abelian statistics, that the order in which you wind them matters, and then you could actually use this, perhaps. Actually, I haven't. I was about to drop on my head. That you can actually try to use those for topological quantum computing. So we're going to discuss a bit of that, hopefully, in the third lecture. Together with, I'm going to discuss ways to actually probe these features in experiments. So let's start discussing what it is. And the first lecture is actually going to be quite basic on the basics of the effect. So first of all, the quantum Hall effect happens at low temperatures, something of the order of liquid helium temperatures. It happens in clean samples, so high mobility, two-dimensional electron gases, and I will explain how you get an electron gas. be calling them 2DAG from now on. And in high fields. So magnetic fields of the order of 1 to 3 Tesla. So I'm going to start describing first 2D electron gas as they were first used, but very recently the quantum Hall effect was also observed at room temperature in monolayer graphene. But one way to obtain a two-dimensional electron gas is actually an assemblage of two semiconductors so suppose you take one layer to grow gallium arsenide, and then another layer to grow aluminum gallium arsenide. So you're going to have an interface in the middle. And in the bottom or in the top, you have a top gate where you can apply some voltage V. Then the bands for the two types of semiconductors, they get bent due to this electric field. Here we have the gap for aluminum gallium arsenide. And here the gap for gallium arsenide. Can you hear me well? Now, the Fermi level, the level you're going to feel all these single particle states of the semiconductor, lies around here. You just have to think about this little triangle as a box, as a one-dimensional box, where you're going to solve for the eigenstates of this particle in the box. And you're going to have wave functions that are going to look like that in this vertical direction. So along the vertical direction, the wave function has some width. But on the plane, it can still move. One can write a full wave function as a product of some two-dimensional component times I'm going to call this psi 0 of z. And this psi 0 will be the ground state wave function for the particle in the well. Okay. Why just the ground state? Well, because we're going to be working at very low temperatures. And the energy gap between the confining, the psi 0 and the psi 1 is very large compared to the temperatures that we're going to be working on. So we're going to be confined to states where the z motion is frozen. It's still there is a width, okay? But effectively, all the degrees of freedom are left in this piece here, phi of x and y. So that's how we trap the electrons in 2 dimensions. Now, in a system like graphene, that you just have one atomic layer, that does the trick for you already. So you just have the motion on the plane. And then you just have to worry about this piece here. Okay, so we've got electrons confined on the plane. Now you cut on the sample a Hall bar. And what is a Hall bar? Now it's the top view of that sample where you attach some source and drain. So you can pass current to that sample. And you have 4 probes where you're going to measure voltages. So with the source and drain, you pass some current, I, and then you probe with the voltmeter. This voltage we're going to call VL for longitudinal drop, and another voltage probe that I'm going to call VH for Hall. You define the longitudinal resistance as just this drop in voltage divided by the current that you passed. And the Hall resistance, VH divided by I. Now, this audience is very quiet. Yeah.
Why do you have to remove this contact from the diagram?
Sorry?
That power configuration, how does it come about in that?
Okay, so suppose that I'm going to take these edges. So let me first, you can cut this, but think about the sample. This can actually be the whole Hall bar. The drain is going to be here. It's going to be a base contact. So that can be the drain attached to the sides. On the other side, you attach the source. So you're going to be passing the current, but the current is going to be flowing in the layer here. So think about it like a sandwich, okay? This is the butter in the middle, so the current flows through the butter. And then you attach your probes on the sides of the sample. Okay. So for example, the Hall probe would go like this. And you would also attach the leads on the other side. You wouldn't use the source drain, the voltage that you measure in the source drain. You actually want to that gives you a more precise measurement.
No, because in the pictures that I see, I always see like
some gates on top, okay.
Things like that.
Because what you actually do, let me redraw this here. Suppose you have a big sample. That was a simplified version. If you have a big sample, you can actually, lithographically, you can put some, you can put gates here on top of your big sample that actually repel the electrons here and makes this a bar. So you can go from a large plane, you can cut off a channel of any width you want. Actually, later on when we discuss tunneling experiments, you can actually pattern your gates in such a way that you can make narrow constrictions, because the electron gas, let me draw the edges of that electron gas. Because as you apply the voltage on these electrodes, you push the electron gas. So the electron gas is in here. And by pinching these contacts, you can actually narrow the constriction, make a very narrow channel. If it's too pinched, you can actually separate into puddles, like a little island in the middle. And so we're going to discuss these geometries. Actually use things like this to measure, to probe fraction charge and fraction statistics in tunneling experiments. Yeah?
You mentioned at the beginning that the Claudio Hall effect appears below 4 Kelvin, roughly. My question is that temperature scale set by the refinement into a 2-deck by this well technique?
That's one of the
so
yes.
so this scale, this temperature scale, is actually a implementation. It's not a fundamental.
No. Like I said, you can observe it at room temperature, because in the case of graphene, you really have only one. Well, it's still the same thing because you have orbitals, but the energy scales are so much higher. They're like electron volts, so that room temperature is basically low temperature physics in those samples. So if you scale everything up, right? If you just make, if you can make all the gaps much larger, like gaps between these states, then there is a question about magnetic fields too, that you want to observe. If you want to see fractions, you want to make sure that as you increase the magnetic field, you're going to have your cyclotron splitting. You don't want your temperature to be much bigger than the cyclotron splitting, otherwise you're going to smear the plateaus. But we're going to get to that.
Excuse me. Can you use metallic samples, very thin metals?
Thin metals wouldn't work for the following reason, because no matter how thin it is, if it's a metal, think about the Fermi wavelength, right? You can count the number of channels, because let's think about this as a number of transverse channels. We can select only one channel by going to just a state, the n equals 0. This would be the other channel, the other transverse channel, and so on. In a metal, if you take a given thickness, you basically divide that you take kF times that distance, tells you the number of channels. And since kF is so large in a metal, you need atomic distances. So if you have kF times A, that has to be of order 1. That means that the thickness of the metal has to be of order lattice spacing. But that actually, in the case of graphene, that's exactly what happens. You have one atomic layer. So that's why it works. But in a typical metal, you're going to have, well, it doesn't matter how thin you make it, you always have many, many atomic layers. Okay. So we're going to be talking a lot about resistivity, conductivity, Hall resistivity, Hall conductivity. So let's define the resistivity and conductivity tensors. So, let me first define the conductivity. The conductivity tensor relates the electric field to your current density. So beta here equals 1 to 2. These are the dimensions, x and y. And you can invert this and relate the electric field to the current density via the resistivity tensor. And rho is sigma inverse, but sigma is the matrix. So since sigma is a matrix, when I invert sigma, I have to invert it as a matrix. So that's how you relate the resistivity to the conductivity. Some symmetries. If I have a sample that is symmetric if I rotate it by 90 degrees, okay, then sigma x has to be equal to sigma y. And also, sigma xy has to be equal to minus sigma yx. This minus sign here is just because as you rotate it, if you rotate the axis, if you draw a figure, you see why it comes about. Now, one observation that I want to make is that in 2D, resistance and resistivity, they have the same dimensions. So just on the side here, remember that resistance is resistivity times the cross-section area, times the length divided by cross-section area. And when D equals 2, these L cancel. That's why they have the same dimensions, rho and R. And they have dimensions of H over E squared. Planck's constant divided by electric charge squared. Okay, let's talk about some experimental observations. Can somebody tell me the experiment by Hall in the 19th century? What was it? What did it tell us? Just the classical one.
The size of the electrons?
Right, the size of the electrons. So basically, you could ask, well, when Maxwell writes his equations, there's an E there. Well, there are charges, they're positive and negative. The question is, okay, in metals, in things that we call metals, what's the sign of the charge carrier? Is it the plus or the minus? So, of course, maybe in another. In a charge conjugate universe, maybe it would be the plus. Okay, you're going to have positrons being the charge carriers. But what Hall did is like he measured. He measured the transverse resistance and just saw which direction what was the sign of the voltage, and then you match the conventions. Okay, you look at your conventions, and then you figure out, given your conventions, what's the charge of the electron. And there, in the classical Hall measurement, you get that the Hall conductivity is NEC divided by B, and the Hall resistance is the inverse. Quick comment here. I just told you that the resistance is a matrix. Okay, the resistivity matrix, the conductance matrix, and here I'm inverting this like that. Okay, we're gonna come back to that in a second. Okay. So it just follows a straight line with magnetic field. The higher the field, the higher the resistance that he measures. Okay, you can think about this as just a Lorentz force. As you apply current, there's a force at X on, because of the magnetic field, there's a force at X on your charge carriers, and that force has to be compensated by the voltage that you apply that gives you electric field. So you have an electric field, a magnetic field, and the total Lorentz force has to vanish in the middle of the sample. Okay, so this was Hall. And then, in 1980, von Klitzen, Dorn, and Pepper and I have some Hall traces that I couldn't put in the computer, but I can show it to you at the end. So that you can actually see real experimental data as opposed to my sketches. But here, if you plot rho xy as a function of B, you see that well, from low fields it looks like Hall's data. It's a straight line, increases with magnetic field. But then something funny started happening. You start seeing these plateaus. Where rho xy was multiples of 1 over n times h over e squared. And at the same time, if they plotted on the same, here, let me draw this on the screen here, for rho xx, that they saw that every time you had a plateau, rho xx was 0, and when you were going between plateaus, rho xx went up and down. But every time that you had a plateau, rho XX went to 0.
The equals are different.
Oh, these are different axes. This is, I'm looking at the traces. I don't have color chart here. Otherwise, these are the rho XX.
No, the ends are different when you have previous and this end.
And, oh yeah, this is the line from this. Let me write M. This is an integer. Let me go with I. Good catch.
And in the linear regime? In the linear regime, rho XX?
Yeah, you mean
So-
linear regime if you pass too much current?
Sorry, no, at the low field regime, and rho XY is initially linear.
Well, there you don't see the plateaus. You start seeing plateaus at large i's, like I equals 4, I equals 5. I don't know actually how high. It depends on the sample. Which plateaus you see depend on how pure the sample is. If you have a very dirty sample, you don't see many of the plateaus. Some of the plateaus you only see in the very best in the high mobility samples. And so where you start seeing the plateaus, that depends on sample volume. Now,
Question, in your left-hand side here, you assumed some kind of high field limit, where you could neglect rho XX.
actually, I was talking about the perfect map.
So rho XX is 0.
Rho XX is 0 here. And actually, that goes back to my question about how can I invert these like that. Okay, this is just the perfect metal case. But let me go back to that question. How can, if I write, for example, let me write sigma xy, and I'm going to do the same thing. I'm going to be cavalier and just invert rho xy. Why is it that we can? Well, remember that I said it was a matrix, but at the plateau, the diagonal elements of that matrix are 0. So if you plug it back in that expression that I wrote over there for the inversion of the matrix, whenever rho xx is 0, rho xy and sigma xy are just the inverse of each other. Okay, try that. Just do that later. So this is very important for you to be able to relate Hall resistivity, Hall conductivity in that way. The longitudinal resistivity, and by the way, a vanishing of the longitudinal resistivity also implies vanishing of the longitudinal conductivity. Lots of interesting things that you can do with a 2x2 matrix. Okay? Now, let me write down the best measurement that I could get a hold of for the Hall resistance. Basically, this number here when I equals 1. Because, or another way to say this, the Hall conductivity is an integer multiple, I should say, where I is an integer, multiple of e squared over h. You'll see why this thing comes about. But you can see here that you can use this as a standard for measuring resistance. Because if you look at the I equals 1, for example, you get e squared over h. So you write resistance in terms of fundamental constants, but not only that, this is really flat. And I can show you that in the data that I brought later, that this is really, really flat. You don't see data. In most experiments, when you talk about you draw your data, you draw your error bars. In Hall traces, usually the error bar is much, much smaller than any line width that you can draw, that you can see the line. Okay? So for example, in this value that is now used for the standard, looks funny, you write too many digits, but that's about the precision. We go to 3.7 parts in 10 to the 9. Now, to appreciate this is a dirty piece of semiconductor, okay, with leads. sticking out, okay? And you put in a refrigerator, you stick something like on top to bring your sample down, but it's a dirty piece of semiconductor. Now, it doesn't matter how clean it is, as we say, it's high mobility, but it's a piece of semiconductor. And now we're talking about measurements that atomic physicists do, right? When they want to measure high precision measurements. And now you go to a low temperature physics lab, and out of that dirty samples you get that. Now, one thing that is very interesting to stress is that you look at this combination, E squared over H. It has units, right? It has units of resistance. But can anybody tell me a non-dimensional combination of E squared H if I stick in another fundamental constant? Alpha. The fine structure constant, right? So if I do E squared over HC, that's related to alpha, right? So if you get another, well, actually, I don't know how you define C in the SI. I think C is defined, right?
It's given.
It's given, right? So if you take that value and you take your R that you measure in your dirty sample in a semiconductor, you get the fine structure constant to that precision, right? And see, 10 to the 9 is actually, now that we got spoiled, 10 to the 9 is, it's fine, but can we go lower? Can we actually, see, if you have of the order of 10 to the 11 electrons per square centimeter, well, if you could just get bigger and bigger samples, maybe you can actually beat up all measurements of atomic physicists using, either trapped electrons or muons. That would be, we can get better and better values of the fine structure constant. And if one could get better and better values of the fine structure constant, one can start addressing very fundamental questions like, is the fine structure constant a constant? Because that's a question that Dyson asked a long time ago. Is the fine structure constant changing as a function of time? But to address these kinds of questions, you need very, very precise measures of the fine structure constant.
Claudio?
Yep.
Is there a reason why rho xx doesn't have p equals 0, that p equals 0?
Oh, just because I'm not going to draw anything like that around here. So I'm just concerned with the high field. Okay. But so I'm not talking about low field. Okay. So this is very interesting. It's integer sets the standard of resistance. Now, in '83, a couple of years later, Stormer and Gossen, they looked at cleaner samples and they observed basically the same thing. However, plateaus, they saw that rho xy could have plateaus. Let me write this here to those new. Where the prefactor for the whole conductance could be a rational number. And again, rho xx is equal to 0, equal to rho sigma xx. So that's what we call the fractional quantum Hall effect. Now you can see fractional multiples of E squared over H. Okay, so let's try to understand how that comes about. The whole thing, the fractional effect. Well, the fraction really is the
So usually you measure conductance and resistance, and there is a geometrical factor between that conductivity and resistivity. How you can get precise measurements if a geometrical factor comes in?
There's a geometric factor that also happens in 2D.
Well, it's usually it's the length divided by the area. Well, the area is also a length. There are two lengths. I read that once that the geometrical factors are gone also. Actually, the resistance is gone. Not the whole resistance is gone. I like to understand that.
Yeah, actually, like I said, they have the same units, but how the geometric factors get out, I think they may go away perhaps only in the large sample limit. Even though it's supposed to be, it's geometric, but there's another scaling. Maybe let's talk about that later, because I'm not 100% sure. I can't remember on top of my head. But there are related questions you can ask. Okay, does it matter if you drill a hole through your Hall bar? And if you actually drill a hole, it doesn't change. Okay, as long as you have a single connected sample. Right. Actually, not even single connected sample. Sorry, it doesn't need to be singly connected. But you can actually drill a hole in the middle of the sample and still get it to have the contact value. Okay, let me give this new a name. This is called the filling fraction. I'm going to take over some of Shankar sticks. I have a heavy hand, I'm breaking all the top. Okay, so how do we approach this problem theoretically? How do we start? So the first thing to start is to write our Hamiltonian. Okay, there's a trade-off. Light chalk.
I'm going back to your chalk.
Okay.
My break one has to go.
I'm going back to my chalk too, for now. So if you write down the Hamiltonian, in the presence of a magnetic field, so the magnetic field is the curl of this thing, and I'm going to take A vector to be the following that you can check that it gives us uniform magnetic field. This is called the circular gauge. Or symmetric gauge. And like Shankar, I'm going to define some variables called Z and Z bar. And I'm going to define derivatives with respect to these variables. Because I want to rewrite that Hamiltonian. That's where I'm heading. I want to rewrite this Hamiltonian in terms of this types of derivatives, which I'm going to call these for short, just partial. These guys just partial bar. This is bar. So if you use these variables, you can rewrite this Hamiltonian. In the following way, where L is called the magnetic length, and L squared equals h bar c over EB. So this magnetic length at high magnetic fields this is the characteristic length scale in the problem. And the higher the magnetic field, the smaller this length. If I solve, now I have this Hamiltonian, I can solve for the wave functions. The eigenstates, right side, and m, they're labeled by 2 numbers. There's some normalization factor, I'm just going to write here. The normalization factor.
This one notation question, E is positive or negative in your mind?
Sorry?
E is positive or negative according to your mind?
E, in this notation, E, the charge of the electron should be negative, because the minimal coupling here is P minus E over CA. This is the charge of the carrier, so the charge of the carrier is going to be negative. But in most cases, it's not going to matter, because we're only going to see E squares coming in. But it will tell the sign of the...
It has E, right? So that makes a difference.
L square.
So when I take square root of that, it matters whether it's negative or not.
Okay, well, it also depends on the convention of B, because if I change the direction of magnetic field, so okay, let's be precise. Okay. Because if I change the direction of my magnetic field, the charge will self-present. But you're right. Let's take a magnetic field. For this LMN, for the gas polynomials, we're not going to get into details here. This is just the full solution of the Landau problem of particles in the magnetic field. We're just going to distill this to get all we need. Okay, but that's the solution. A couple more things that we can do. We can look at the angular momentum of well, some states, but first we have to define the angular momentum operator. In terms of these variables, L is h bar, z partial z, minus z bar, partial z bar. What it means is that every time that you have a z, you have angular momentum h bar. Every time you have a z bar, you take the derivative, you get rid of one z bar, you put it back, but it comes with a minus 1. So z's have positive angular momentum, z bars carry negative angular momentum. Now let me focus. Okay, I'm going to focus at the low Landau levels, which means I'm going to look, for example, interesting if you set n, if n is equal to 0, this is a constant, it disappears. So your wave functions are powers of z. Okay, and then there's this extra Gaussian factor. But in general, wave functions, your peaks at a distance Rm equals square root of 2m times L. from the origin. So let's draw these orbitals. So here's the origin. Then, as a function of m, the orbitals go out. So the wave function is centered around some radius. And this Rm here is this one, 2m times L. So the larger m, the larger the orbital, and the larger m, the larger the angular momentum. Okay, so these are the orbitals, but what about the spectrum? The energy spectrum depends only on n. Where omega c is the classical cyclotron frequency, TB over MC. It's basically the period that if you put an electron in a magnetic field, it's going to go around. Another thing I want to say here is that as a function of the energy, you can write the density of states. And what it is that you have states only at energies that are spaced by h bar omega c. The first one starts at h bar omega c over 2. Second one, h bar omega c times 3/2, and so on. Now there are many states sitting at each energy. There's a huge degeneracy. Now I'm going to calculate this degeneracy for you. Okay, that's why I talked about this radius, the distance at which the orbital is from the origin. For a given n, we have that the radius of the orbit labeled by m is this. So you could ask, well, what is the maximum m that you can fill in a sample of radius r? Well, if the sample has radius r, the r of m maximum, because this grows with m, has to be equal to the radius of your sample. So I'm going to use a circular sample here. So r is the radius of the disk. So we can calculate what n maximum is. I go to that formula and I square it. So n maximum is going to be r squared divided by 2l squared. It goes by 2 pi, pi, on top and on the bottom. Pi r squared is the area of the sample, divided by 2 pi l squared. So if I give it a sample of a certain area, that's how many orbitals I can fit in each Landau level. Another way to write that number and you just massage that number a little bit. Let me say I multiply it by the magnetic field on top and on the bottom. And I do that because magnetic field times the area is the flux through the sample. And if I go back to what L squared was h bar c over EB. The B cancels. Phi H bar is H. Have phi divided by HC divided by E. This is the quantum of flux. So we get that the number of levels that you can fit in that area for each lambda level is the flux divided by the quantum of flux. So this is the number of flux quanta that are going through that area A. Okay, I'm going to take a pause to drink some lemonade. It's a hint. Yeah.
So if you're imagining spin polarized electrons,
So, yeah, go ahead. You fine?
you're imagining spin polarized electrons.
Mhm.
So you're forgetting about spin.
Yeah, I'm forgetting about spin. So you can put back the spin degrees of freedom. In the first approximation, you attempted to say, well, the magnetic field is so large, all spins are polarized. But actually, the ratio, if you look at this energy scale, for example, for the gallium arsenide to that, omega C, it's linear in B, so it increases with B. The Zeeman splitting also increases linearly in B. So you ask, okay, what's the ratio of these two? It's a factor of 60. So this energy scale is much larger. So if you go to very low temperatures, it's okay to think that the magnetic field is spin splitting. But actually, when we look at the, for example, integer Hall effect, when you see the 2 is square over H, it's not that you're filling up the second lambda level, the orbital one. It's actually you're seeing the spin, because the splitting between the spin levels is much smaller than the H bar omega C.
What you mean for very low temperature?
Okay. So the temperature has to be, for example, smaller than that splitting, so that you can resolve the lambda levels. So that's one limit. The other limit is this splitting between, for the Z component of spin, Z component of the trapping of the electron gas. So that's the other constraint.
Maybe you should mention that you pick a certain gauge for solving this problem.
Mm-hmm.
They've got next circular orbits. Sometimes it's useful to have other gauges for the orbits running up and down the sample from the draw.
That's right. So Shankar's comment is that I chose to work on this in a gauge that the orbits look like circles. Now, see, there's this huge degeneracy here. One of the, all these degenerate states, I could, for example, you could imagine I take these degenerate states and make other linear combinations of them. They are still going to be good eigenstates of energy. But the wave functions are going to look different. They're going to have different shapes. The orbital is going to have different shapes. All this can be done also by just having started from a different gauge. I took this gauge, if you remember, when I wrote my vector potential, I wrote it like this. I could have written something else that gives the same magnetic field when I take the curl, for example. Something like this. By picking different gauges, your wave functions look different. So instead of looking like circles, they look like spaghetti. Right? They look like just straight lines along the x direction or along the y direction, because I could have put minus by here and 0 there. So the form of the wave functions depend on gauge. But if you ask, okay, physically, where is that large freedom of choosing gauge comes about? Well, you have a very highly degenerate. Each of these levels, for a given n, you have many, many m's. So once you have that large degeneracy, you can mix your states. Okay. Any more questions, or should I wait for the next lemonade break?
I have a question.
Uh-huh.
Do you always have edge states?
You,
And does
okay,
that
that's
depend
a
on the
good
grid?
one. Let me give the right answer, which I think is the right answer is for a real system. In a real system, you always have an edge. And these Landau levels we've been discussing is for a closed system. But as you come close to the edge, there's a confining potential that grows. At one point, that the confining potential is going to meet your Landau band. And you're going to have a state that's going to be running along the edge, where you're not going to have this, if for example you fix your chemical potential, and then you have this Landau level below the gap, it's completely filled, but as you cross the chemical potential, those states are going to be filled before you meet and empty later. That's what sets the radius of your sample. And you're going to have these chiral states where the electrons are going to go around because of the magnetic field. You're going to have edges. Now, something that's very interesting, and that's a theory land, you could ask, well, what happens if you put your system on a torus, right? Well, if you're a theorist, you can study it in any geometry you want. You just solve the problem in periodic boundary conditions. That's one way to put it on a torus. In the fractional effect, and hopefully I'll be able to comment a little more later. In the fractional effect, the ground state of the system, okay, once you put interactions that lift up this huge degeneracy and you get a good ground state, the ground state is degenerate if you put on a torus, and for example, for filling fraction 3, the ground state degeneracy is going to be 3-fold. But that's a different kind of degeneracy than the ones that we encounter, for example, in semiconductor physics when you have a degeneracy due to symmetry. Symmetries can be broken. This degeneracy is related to the topology. We put it in a torus, we're going to have a 3-fold degeneracy if the radius of the torus is very large. If you have 2 holes, if you have a torus with 2 holes, the degeneracy goes to 3 squared. And this is some of the features that I hopefully would like to comment towards the end. But that's where we see that the quantum Hall effect, besides the observed plateaus, it's a source of many, many ideas in condensed matter physics, which are really novel and it's still unexplored. Okay. So let's see. We have these Landau levels. We have the degeneracy. I haven't told you yet anything about why the plateaus come about. So let me give you some notion of that. Why? Okay, so this is just the expression for the whole resistance, the classical one where n here is the electron density, which is the number of electrons per unit area. So let me write this as NE, EC divided by the area, this is A, in EC. This is the flux. And let me write flux divided by NE. EC I'm going to write as kilometer, whatever I'm doing. That's our flux quantum, right? AC over E. So I just want to re-express this in terms of the number of flux quantum and the number of electrons. Divide by phi 0, divide by phi 0. And phi 0 divided by EC is h over E squared. And this is the number of flux quantum. Or sigma xy is equal to E squared over h plus E over n phi. So you can relate the whole conductivity to E squared over h times the ratio of the number of electrons in your sample and the number of flux quanta. So this ratio is going to be very important, and we call this the filling fraction nu. Okay, so what is it that happens that is special for the integer Hall effect? Well, that's when this ratio is integer. But let's see what is it that happens that is interesting when this ratio is an integer. So I'm going to give you some qualitative hand wave argument for the quantization of the Hall conductance before we get to the real. So let me turn the picture that I draw for the density of states a function of energy. I'm going to actually turn it around and put the NE here and the E there. So I have these energy levels with many, many states, highly degenerate. And this filling fraction, as I start to fill this state, what happens is that when I put my Fermi level here, I fill all of one of the Landau bands. If I had moved my Fermi level here, this one would correspond to N over N phi equals 2. This level here would correspond to NE over N phi equals 1, and so on. So whenever this number is an integer, I'm putting my Fermi level, the level in which I fill all the states, in the middle of the Landau bands, in the middle of the gap. Well, you could say, well, why can't you vary it continuously? You can put, if you vary the Fermi level continuously, for example, if you want to see a ratio of electrons per flux, which is not an integer, just put your Fermi level here. And actually, even though the chemical potential is fixed, you can vary the number of electrons in your sample. So we see that there's something special when this ratio is 1, but we don't see why it's robust. Why is it that as you vary the magnetic field changes the number of flux in a sample that has a fixed number of electrons. So why is it that there's something special there? So the hand wave argument that, let's live with it for now, but I'll give you something better later, is that once you put this order is going to fill a lot of states in the middle that will act as reservoirs. And as you try to change the chemical potential, try to change the magnetic field to change the number of fluxes, your chemical potential moves, but it's only filling states which are localized. They don't contribute to the conductance. So as you move this guy, you change the magnetic field, you move this filling fraction, you're filling out localized states. Something happens only when you go through the center of the Landau band. So what happens is that, as a function of B, your sigma xy. Plot rho xy. It's going to go through a plateau where, as you vary b here, that's when you're in the middle. And you're feeling states that don't matter because they're localized. Only when you go through this peak that it matters. Okay, let me give you now an argument about the exact quantization of the Hall conductance. If something is quantized to a point in 10 to the 9, it must mean that there is some fundamental principle underlying this. It's not just a miracle of some miraculous cancellation. And this principle is gauge invariance. Plus the existence of something we call mobility. Yeah. Which is due to disorder, meaning that there are some states there which do not conduct electricity. So let me give you one of these arguments. So consider a disk. That has a hole in the middle. And suppose that somehow you pass current, there's some current I flow this disk. Okay, so there's a current I. And you measure the Hall voltage. There's a magnetic field B here. Now, through this hole, suppose that very slowly, adiabatically, you insert some flux, some Q flux one, but you do it very slowly. And now we're going to have another lemonade break. You guys to help me out. What happens when you insert flux adiabatically? Okay, I'm asking the question. It's much easier if you ask me. But since you don't ask me, I ask you.
Yeah, the Faraday effect.
Faraday effect. Perfect. Let me write to your dean and tell you that Professor Coleman asked about the Faraday effect. Okay, well, what if the system, let's say, you say you're going to insert the flux and you're going to generate an electromotive force, right? That will happen too. But say, I want to think about this thing quantum mechanically. And at the end of the day, suppose that I'm going to insert an integer number of flux quantity. At the very end of the day, what is it that I can do to the system that I could not do if it were a multiple of flux quantity? First of all, let me say one more thing. because of the hole, is there any magnetic field that, that at the end of the day, when you stop changing your flux, we have some flux here, is there any change in the magnetic field because of the flux quantum? No. Oh, right. So there's no, it's just like the Aharonov-Bohm effect, right? You insert flux through the hole, there's nothing that happens in the sample. And if you insert an integer number of flux quanta, you can gauge it out. You can completely take it out of your Hamiltonian. Your Hamiltonian goes back to exactly what it was. Your state, however, may not land exactly the same state you were. You're going to be in an eigenstate, since you did it slowly. You start in an eigenstate, you insert this flux adiabatic, you change your Hamiltonian. At the end of the day, you're back to the same Hamiltonian, because this is an integer multiple of the flux quantum. But you may be taken to an excited state, not not the same state you were. Okay. Oh, the time scale, good question. Okay, you have a time scale to insert this. Then, as in the adiabatic theorem, right, you need to make things slow compared to some a scale that's set by the gap. In this case, since our system has a gap, that will bring the scale for which things are slow. So if I look, whatever the energy gap here, if it's the integer, it's h bar omega c. If it's the fraction, it's going to be the multiple of 3 squared L. That energy scale, h bar divided by that energy scale, tells the time scale, and as long as I do it much slower than that, I'm fine.
So it could be end of the week or end of the month.
Yeah.
End of something.
End of something. End of the school. So turn on the field now, so by the end of the week we're done. Okay.
Can I ask something?
Mm-hmm.
The width of the plateaus, are they equal to the increase of the magnetic field that is equal to the difference in the chemical potential between the two levels? Experimentally, is the width of each plateau connected to the difference in the chemical potential between the one level and the other?
Oh, you mean this width here?
Yeah.
Okay, it's actually related to the amount of disorder. For example, if you have a perfectly clean system, you wouldn't have the quantized Hall effect. So it depends crucially in the, you need disorder to give you the plateaus, because you need this reservoir of states. But it's not, at the same time, if you have too much disorder, you destroy the quantum Hall effect. So it's
So the theory works for the centers of the plateaus, or so what would be
you mean that argument that I'm working on, where it works?
I mean the thing for which the ME over M5
Okay.
what integer?
See, I have two assumptions here. One is gauge invariance, that's what I was working there. And then there's a mobility gap. So I'm going to be assuming that I'm within this mobility gap. And how much change in magnetic field I can tolerate before I go to the next plateau, that depends on the size of on this mobility gap. Now, the only thing I can argue here, I'm not going to be able to show which fraction, what's the value of the resistivity. The only thing I'm going to be able, with such a generic argument, one thing you have to appreciate is that when the argument is too generic, we often cannot say something very specific, like, what is exactly the conductance? What we're going to be able to show is that it has to be some rational number times e squared over h, but I don't know which rational number. Okay? Yeah?
How many states are there at the center of each round of band? I mean, the extended state, is it 1 or is it a finite number?
Oh, there's a finite number here. Sorry, in the center,
In the center.
there's a large number, because in the limit of the clean sample, there's actually, when we calculate this degeneracy, it's the number, it's the total flux over your sample, divided by the flux quantum, the number of flux that penetrate the sample. So that's the number of states that are exactly that energy. Once you turn on this order, what happens is that instead of like getting spread out, the delocalized states remain in the center of the band, but then you create some localized states away. So the only delocalized states are the ones in the center of the band.
So the number of delocalized states depends on the amount of disorder you put in.
Right. So it's the amount of disorder will control the fraction of the ones that remain here and the ones that go out there. Yeah.
What's the limit, just to throw it, what's the limiting value for clean system of the OXY versus bigger?
Oh, the clean limit, if you restore translation invariance, then you can argue by translation invariance that the only thing you can get is the classical result. Okay? Because, and then you can do, because since you have no disorder, you can always boost and go to the center of mass of the electron. And then you can go from there to argue that the whole resistivity has to be linear indeed. Now, what happens when you put disorder? So that's a good question. Why is it that in the clean limit it's so special? Because in the clean limit you have translation invariance. You can always boost and go to the rest frame of the electron and see the system as it was before. If you have disorder, you broke translation invariance and you can no longer do that. Okay.
We have 13 more minutes.
Okay. Give me 3 to finish that argument.
And then we go to this section.
Yeah. Let me just see, a couple of things here. Let me write to you a relationship between Okay, let me just sketch this. If I want to calculate current, I can write a current as the C variation of the current of Hamilton with respect to fractal differential. That's how I define current. If I just using this relation, I can derive a relationship between how, if I vary the flux, I change the ground state energy, or the energy of my system, right? Of the ground state of this of the whole system, the many-body problem. So I'm not going to write details of the derivation, but you can write the current in terms of the derivative of the energy with respect to the flux with a C. Now, we said that if you have a change in flux, which is some integer number of the flux quantum, you can actually, at the end of the day, gauge that out. And the only effect is that you took your system adiabatically from one state to another, but an excited state. Now I'm going to use the second assumption, that there's a mobility gap. If there's a mobility gap in the middle of the system, right, that those states are not current carrying, which kind of excited states can I be left with at the end of the day? Well, these correspond, the excited states will correspond to bringing charge from one edge to the other through the external circuit. But that energy of that excitation, I know how to calculate. Because suppose I bring some charge from here to there. I know that the energy of bringing, for example, an electron is E times the V. So that's the energy of the excitation. What about if I bring P electrons? If I bring P electrons, then I have PE times P Hall. But I know for sure one thing, that Q, this Q that I insert, to be able to gauge it out, better be an integer. If the charge went through an external circuit to go from one edge to the other, that P better be an integer. Because the external circuit doesn't, the only thing that it knows about is electrons, right? So if I know,
why I cannot just increase the structural amount, the infinitesimal amount of current? And if I increase the flux like this, why I cannot do this?
Because when you increase the flux infinitesimally, or because, see, you can put an infinitesimal flux, but if you just put an infinitesimal flux, I cannot argue that we can gauge it out completely. So it has to be a multiple of the flux quantum, so you can gauge out completely and say that you restore your Hamiltonian to the original Hamiltonian. So the flux has to be an integer multiple of phi 0. Since the charge is going to an external circuit, it has to be an integer multiple of E. Now I use my relationship between the the current I and the, so I can write I equals to C delta E divided by delta phi, which is equal to C PEVH divided by Q, the flux quantum HC over E. The C will cancel. That's actually good, right? Because there's nothing here that you would expect to be relativistic. We have a C, we have the E squared over H, and we have the VH. This current that I wrote here is actually, it is the expression for the Hall current. So I just relate the Hall current to the Hall voltage. And what is this here? Well, this is sigma xy. So we found out that sigma xy has to be a rational multiple of E squared over H. A very generic argument. We cannot say anything about this numbers P and Q. The only thing we can say is that they're integers. So with this very generic principles, we can show that the Hall conductivity has to be a rational number of E squared over H. Yes?
So where did you use this linear if the Hamiltonian doesn't change?
I use the fact that what didn't change?
The Hamiltonian doesn't change.
Oh, because at the end of the day, when I argue that, this is my delta E that I want to write. And I want to bring my Hamiltonian exactly to the same Hamiltonian so that I can discuss the energy change at the end of the adiabatic process. So I want to have exactly the same Hamiltonian, so now I can compare initial and final. And for that, I need an integer number of quantities, so I can bring my Hamiltonian to the same initial and final case, so that I can make an argument that if there are the non-current carrying states in the middle, that I will have to, the only way to write down that excited state is by bringing in an integer number of charges through the external circuit from one edge to the other.
So, I guess it's over for the discussion. We only have 5 minutes left, but anyway, just go on asking questions.
Let me get in first, and then you.
In this argument, can we set up, can we choose an arbitrary Q and always say, just choose equal to 1 and always.
Okay. See, when I said that the argument is very powerful, but to the expense of we cannot say anything about the P and Q.
We can choose the flux we can.
Yeah, but let me ask the following. Suppose that you choose Q to be 1. Let me tell you exactly what happens in the fractional effect. Okay, even though we haven't got to there, it's going to help. In the integer effect, you can take Q to 1 because you can then just pass an electron to the other side. But in the case of the fractional effect, the excitations have 1/3 charge. But 1/3 charge, so at the end of the flux insertion, you take the system to, because you can still gauge out, you don't need Q to be able to bring Hamiltonian to the original Hamiltonian. All you need is 1, for example. But you bring the Hamiltonian back, you're going to be left in an excited state. But in this excited state, you just create quasi-particles that will have charge 1/3, say in the U equals 1/3 effect. And I'll show that in the next lecture. But 1/3 charge can exist in the Hall liquid, but it cannot exist in the external circuit. So even though you're fine with regards to the Hamiltonian, it's back to the original value, you're in an excited state of that Hamiltonian, but there's nothing you can do to transfer charge to an external circuit. You can't, because you cannot pass to an external circuit something that's not an electron. So you need to do a couple more times. You need 3 flux quanta, because as you insert 3 flux quanta, you generated 3 quasi-particles. 3 quasi-particles that charge 1/3. You can put them together to an electron, and now you pass them to the other side of the sample through the external circuit. So you're right that you just need 1 flux quantum, but the problem is that you may need more to be able to do the second step of going through the external circuit. Oh yeah, I forgot.
Yeah, all right.
So, is there, do we begin with the current around the loop or not?
You will begin with the current if you have the voltage, right? Because there's a relationship between the current and the voltage.
So where is the mobility gap then? And then it is down.
Oh, the argument for the mobility gap is that suppose that by inserting the flux quantum, like in that example I said, that you have some 1/3 charge here.
Yeah.
You want to make sure that, or even beyond that, more simply, I want to pass my current to the external circuit as part of this argument. I don't want to, I need this mobility gap so that I can argue that there's the excitations that I create by putting the flux are not excitations that are in the bulk. They are excitations that are on the edge of your sample. And if I didn't have that gap for current carrying states, I could argue that for example, in the linear regime, if this voltage is very small, and it's going to be small in an experiment. See, this energy is very small. I want to make sure that the only way that I can write an excitation that has a small energy involves moving something from one edge to the other. If I can make it in the bulk with a small energy, then the argument fails. So that's why you need that in the bulk there is a gap, and that any excitation that I get in the bulk is going to cause the energy gap, which is much smaller than that. See, here, assume that VH is very, very small, the smallest you can make.
Because there was another question over there. Okay, that was the other thing. What?
At the beginning of your lecture, you consider two-dimensional electrogas, right? So I am thinking about the problem of electrons pushing quantum critical point. Sometimes there are some experimental evidence that the system's change is three-dimensional character, two-dimensional character. So could you give me any comments about how to apply this idea to quantum criticality in electrons, or which kind of information would effect can give?
Actually, what is the mechanism for this dimensional reduction? I don't know.
Relation to the coupling of the phase, because when you coupling, the electrons is induced below the temperature. So
you say because you have a correlation length that's growing and it's coupling all these planes and they behave collectively?
Yes.
But do you still need a thin sample because your correlation length has to be bigger than your sample size, right?
It doesn't replace decoupling.
They decouple or decouple?
They decouple.
Okay.
So initially it is a 3D parameter. As you lower the temperature, due to frustration, the nearby plane decouple. So it becomes a two-dimensional system.
But are these magnetic systems or they also carry current, right? Okay. The problem with the heavy fermi, I can tell you one. It's the fact that they're actually heavy. Okay? Remember the cyclotron gap? It was EB over MC. Actually, next lecture we're going to talk about projection up to the first Landau level to discuss the first fractional effect. One of the things you want is to push things down to the lowest Landau level. For that projection to work, you need a huge gap, okay? At least compared to your temperature scales. One way to do that, as a Gedanken experiment, is that you take the mass to 0. That will shoot up the cyclotron gap very high. But if you have a system that's already your band is very flat already because of the heavy mass, it means that you would need huge magnetic fields. So maybe the answer is maybe possible, but you may need a humongous magnetic fields.
Going back to the issue of disorder and the single XY versus VH plug. So in order to take the transaction invariance, you only need one impurity. So is the clean limit then singular in that sense?
That's a good question. Okay, well, it is singular because you break the translation invariance, but then you could ask, suppose that you could do an experiment and you put a single impurity, and you ask what's the Hall trace. My intuition is that it's probably going to look just like the green bar. That's my intuition that